This is the second video on gravity, and I'm going to derive some of the equations that we're going to use. I use notes for this now because sometimes I tend to forget not equations but where I am in the derivation of them. We're going to be talking about only a vertical trajectory, or a vertical orbit if you like, such as the moon's first orbit when it went more or less straight away from the Earth, because it simplifies things. You need only then two dimensions, the space dimension and the x dimension. And to derive the equations to explain how gravity works, you only need one dimension. If you can explain what causes something to drop, then you can explain how something gets into an orbit when you into a circular orbit when you have more dimensions. We're going to ignore the time dimension because the velocities are not large enough to make a very large time dilation or increase in mass, and the effect of the mass increase on gravity is a long-term effect, and I believe that it's that causes orbits to change from elliptical to circular, to broader elliptical and then to circular orbits. So we're concerned about what causes gravity, so I'm going to leave the time dimension out of it for the time being. Now, in order to, this is the moon in space, but it's also has an x component, and the x coordinate represents the velocity, and the y or the r component represents the separation in space, and the vector sum represents the total energy. So if you like, this represents the total energy, this is the kinetic energy, and this is the potential energy. Now, in order to represent the constant energy, we have to use the theorem of Pythagoras, and we can say that the total separation, which I'm going to call R0, which is the maximum value of R, the separation, it's the height to which the moon went on its first orbit. And this squared is equal to, at any time, is equal to R squared plus x squared. That's Pythagoras, and it's the equation. It's going to be one of our simultaneous equations that represents the constant total energy. This shows the enforcement of that law. But there's also a constant momentum, and that's obtained from the velocity, which is called v0, and this is equal to the velocity when x is equal to 0, and the body is at there's no separation between the bodies in space. You get the maximum velocity, and that you get the velocity squared is equal to the sum of the squares of the velocities in the two different dimensions. So that's equal to dr by dt all squared plus dx by dt all squared, and that represents the constant velocity. And by solving those two equations, we can find out how the location of the moon, or whatever body it is, varies with time. So if I drop this pen, its location at any time is given by the equation we get for the variation of r, and its velocity at any time is its velocity as obtained again by solving these equations. And there's a very simple solution. We don't have to get into very complicated mathematics here, because we can see that if the body is going round at a constant velocity, it's going to actually, the solution is going to be simple harmonic motion, and we can say that r is equal to R naught times the cosine of the frequency times the time. I hope you can see that. It's not a very broad pen. It's a dry erase marker, fortunately. Now the velocity, which you get by differentiating this with time, is equal to the maximum velocity times the sine of omega t. Omega is the frequency, and it is equal to the maximum velocity maximum velocity divided by the maximum distance. That's the frequency in radians per second. There's also, I prefer to think of the reciprocal of frequency, which is the period of the system. And the period is equal to, which I use the Greek tau, but that is equal to R naught over V naught. And the frequency is the reciprocal of that. So we've got a solution here to our equations that we can use in order to see how the location of R varies with time and how the velocity changes with time. Let me get my eraser. And then I will show you how the acceleration varies with time, and that is going to be of interest because we already have equations for that from Sir Isaac Newton. If you differentiate the velocity, you get, I'm sure you remember how to differentiate. If you differentiate V equals V naught sine omega t, if you differentiate that, you'll get, this is the product of two variables, so the derivative of that is this times the derivative of that plus this plus the derivative of that. And that all comes to V naught, the acceleration is equal to V naught squared over R naught times the cosine, actually the minus sign in here, cosine omega t, which is very interesting because that, of course, is the well known as the equation for centrifugal force. So that the acceleration is equal to the centrifugal force in the circular orbit in space and in the x dimension, multiplied by the cosine of the frequency times the time. And this looks very different from Newton's equation. And the reason it does that is because we are dealing with the variation of the location of the velocity and the acceleration with time. And Newton did this in relation to distance. His equation, as you may remember, and I dropped my thing, that his equation is equal to, acceleration is equal to the mass of the two bodies, the mass of the Earth in the case of the Earth, times the universal gravity constant over R squared. And these two give identical results when the cosine is 1, because when the cosine is 1, then the acceleration is V squared over R. This is for the top of the apex of the vertical fall or orbit, and that is equal to the centrifugal force, which is equal to Einstein's force of gravity, because Einstein said the force in a circular orbit, and presumably also when something is not moving, that the force is equal to the centrifugal force. That's why bodies stay in circular orbit, and so they're the same when this is equal to 1. This is also equal to 1, but but it's not equal to 1 at other times. Because one thing that's pretty obvious from this is that as r gets smaller, when something drops, r gets smaller, the acceleration increases. And this is well known as the inverse square law. But in this equation, when the when time is 0, the body is at the top of its fall, and as it falls, then you can see the cosine reduces and the acceleration actually gets smaller. So I say that as I drop this, the acceleration gets very, very imperceptibly smaller because the distance between here and the center of the Earth is so similar all throughout its entire trajectory that you wouldn't see any difference. But if you had something dropping from the height of the moon to the Earth, there'd be a considerable difference. So there's a considerable difference between the equation that I've derived and Newton's equation. And it would be interesting to perform an experiment just to prove that I'm wrong, or possibly to prove that I'm right. But we'll talk about that on another occasion. I just want to point this out now. As a result of this too, and I will point out on a later video, exactly what kind of correction you can put to this to give his result the same as mine. Actually, it's not too bad. The correction is that you multiply by r cubed divided by r naught cubed. Which is a correction that says that when r is equal to r naught, namely at the top of the trajectory, then this is 1 and my equation agrees with his. But as something falls, r3 remains constant, r0 remains constant, but this changes. So as the body falls, so this applies only to a direct a straight fall. It doesn't apply to an elliptical orbit or to a trajectory that's on a curve, but it applies to a straight orbit. This correction would give Newton's equation the same answer as mine for a straight fall. But we'll discuss that all much later. So this is, you apply the correction that I proposed, you get a new equation for Newton's equation, and you see that the acceleration increases with the distance from a body linearly, because r naught is the maximum distance when the kinetic energy is 0, the energy is all potential. So this, for a given system, any given system such as the Earth and the Moon, or for dropping this pen, then the acceleration increases with the distance for a given system. Now Newton's equation is correct for comparing systems. When you have different systems, as he would be dealing with when studying astronomy, that you're comparing different moons and planets and stars, and so where the system differs and there's different amounts of energy, then this equation applies by comparing two circular orbits, for example, of different radii. Then this equation applies. So that if you take this pen motionless at this point, which is one system, and then take this pen motionless at this point, which is a different system, then the ratio from here to here will give you a greater acceleration here than here. In other words, it follows Newton's equation when there is no vertical movement, or when you are in different systems. So that's essentially the difference between this theory and Newton's equation. That's enough for gravity 2.